Hello. Thank you for your interest in this course on the basics of solar energy. This is part of a larger specialization on solar energy design and installation. I will help guide you through the major sources of energy, how solar panels, also known as photovoltaic panels, convert sunlight to energy, how we calculate and understand efficiency, and the major components that make up a solar photovoltaic system. You will also learn ways to measure and calculate power and energy, determine the energy needs of a site, and the basics of sizing a photovoltaic system to meet an energy demand. We'll also go over the discovery and history of solar panels, different applications of solar energy, and look at some market trends and the future outlook for solar energy. You will learn about the stakeholders involved in the field of photovoltaics, the major financial models used in on-grid solar, and requirements for photovoltaic installers, including training and certifications. Finally, you will have the opportunity to design your own basic photovoltaic system that will meet the electrical needs for your location. There may be some unfamiliar technical and mathematical aspects in this course, but we'll provide resources to gain a bit more background if you need it. You will need to do some basic math, such as addition, subtraction, multiplication, division, and working with percentages and fractions. So you want at least a basic calculator when working on some of the learning activities. I look forward to helping you meet your goals, whether it be a certified solar installer or a curious solar citizen who wants to learn a bit more about solar energy. Hi, and welcome to the first lesson in this course. In this segment, we'll be discussing primary sources of energy, energy conversions, and total energy reserves. We'll also be differentiating between renewable and non-renewable forms of energy. Lastly, we'll describe the invention and progress of photovoltaics. Let's begin by looking at different forms of energy that exist and how we can convert them. Energy exists in several forms and can be converted from one form to another. Examples include conversions among heat, light, chemical, mechanical, thermal, and gravitational energy. Practically, an example might be burning of wood or biomass. In this case, the chemical energy contained within the wood is burned and the products are both heat and light. The conversion is chemical energy to heat and light energy. Another example would be photosynthesis, where plants absorb solar energy and convert that into chemical energy. Those are only a couple of the examples of energy conversions, but there are many more. Fundamentally, all energy conversions have a starting point, which we'll think of as the primary energy source. There are only a few primary energy sources available on Earth. The first is the sun, which is both the largest source of energy as well as the largest source of possible conversions. For example, we have biogenic resources, which come from photosynthesis that include wood and other plant matter, as well as the products such as ethanol and biodiesel. Under the right conditions, those same photosynthetic products are converted to energy-dense fossil fuels, such as coal, crude oil, and natural gas. There's also the heat and light of the sun, which are directly used in photovoltaic and solar thermal applications, as well as all of our weather events such as wind, waves, precipitation, and running water that can all be harnessed and converted into other forms of energy. Another primary source of energy is the Earth itself. Contained within the Earth are minerals like uranium, which are used in the nuclear energy industry. Another source of energy within the Earth is geothermal, which originates from the heat contained within the Earth. The third form of primary energy is the actual Earth's movement and satellite movement within the solar system. The moon moves around the Earth, which is partially responsible for tides and tidal energy. The force of gravity resulting from Earth's orbit and attraction to the sun provides some forms of energy that we can also use. We're going to look more closely at solar panels and how they convert that sunlight into electricity. By the end of this lesson, you should be able to describe the major components of a solar panel, distinguish between the different materials that are commonly used in solar panels, describe how a semiconductor functions, and recognize new and emerging types of solar panels. The most common type of photovoltaic we see in the world today are made of the element silicon. The solar cell is the basic unit of a photovoltaic module or panel. A single solar cell produces about a half a volt of electricity and up to about 8 amps depending on the type of cell. That's about 1/3 the voltage of a AA battery. The solar cell consists of a piece of silicon with contacts or electrodes that are put across the surface and on the back. Often you'll see many smaller contacts connected together by a few larger contacts on the cell's surface. Now, a half a volt isn't going to be able to do very much, so cells are connected in series to create what's called a series string, thus increasing the voltage. This is similar to how batteries are put together in electronics, front to back, so they add up to a higher voltage. So for example, you might put 2 AA batteries into a flashlight, which increases the total voltage to 3 volts. The voltage of the series string is simply the sum of the half volt cells, which in this illustrated example of 8 cells would be 4 volts. The series string is laminated to backing material, sealed in a weatherproof plastic coating, and then a cover glass is placed on top, often with an aluminum frame around the edges. This assembly is called the photovoltaic module. It's also referred to as a solar panel. The typical solar panels you see on a home or a commercial building will usually be a lot bigger than our simplified example here, and may contain series strings of 60 or even 72 cells per module. When designing a photovoltaic system, photovoltaic modules, also known as panels, will be put together in what's called a photovoltaic array. Just like when the series strings of cells are wired together to make the module, we can also wire modules together in series to increase the voltage of the overall system. In this case, our 4-volt modules would create 16 volts when connected together in series. An array of modules is what you're looking at when you see a roof-mounted photovoltaic system, or even a ground-mounted system. So the solar cells that make up commercially available modules are made of silicon. There's some variety to the type of silicon and how it's processed that impacts the overall cost of production and the light to electricity conversion efficiency of the module. The least efficient, but cheapest to produce, is amorphous silicon. It has an efficiency of about 5 to 7% and is not commonly used for commercial photovoltaics. However, you've probably seen amorphous silicon on the surface of pocket calculators and other small electronic devices. Most commercially available modules are either made of monocrystalline silicon or polycrystalline silicon. Polycrystalline silicon, which is sometimes also referred to as multicrystalline silicon, has a flaky appearance. It's a little less efficient in converting light to electricity than the monocrystalline silicon, in the range of 15 to 17%, but it's cheaper to manufacture because it's not as pure or energy intensive to produce. The silicon is deposited in a chemical vapor process that forms multiple crystals, giving it that characteristic flaky-like appearance. The ingot can then be sliced into wafers to make photovoltaic cells or serve as the stock for making monocrystalline silicon. Monocrystalline silicon, or single crystal silicon, is more efficient in converting light to electricity in the range of about 15 to 22%, but it's also the most expensive to produce. So the silicon must be first melted down, and then a seed crystal is attached to a rotating thread or rod. That silicon is then grown around the seed and is slowly pulled up into what's called a boule, which is one single crystal piece of silicon. That round boule is then cut into thin slices, and that round shape often results in cells with rounded corners or rectangles, often seen in those monocrystalline modules. The overall appearance of silicon is uniform, flat black, and non-flaky. So how does the silicon actually convert sunlight into electricity? Well, it's because silicon is a semiconductor, meaning that electrons can flow or conduct under the right conditions. In both monocrystalline and polycrystalline silicon production, there's also a doping process where impurities are specially added to silicon to slightly alter its conductivity and its charge. The typical dopants are boron, which creates a positive charge, or phosphorus, which creates a negative charge. The positive charge is referred to as P-type material, and the negative charge is referred to as N-type material. Let's see what this looks like in the cross-section of our solar cell. As we work down from the surface of the solar cell, there's a top anti-reflective coating. There's also the top contacts that will carry the electricity generated from the silicon out of the cell and into the circuit. Even though we're showing them as two layers, the next two sections are actually one piece of silicon. The upper part is the N-type region that was doped with phosphorus, and the lower part is the P-type region, which was doped with boron. The area where the N-type and the P-type regions meet up is referred to as the NP junction. Lastly, on the bottom, there's another contact that will complete the circuit. So electricity flows from the top through the system and then back to the bottom of the solar cell. When photons of light hit that photovoltaic cell, electrons are ejected from the N-type region, move into those top contacts, through the circuit, creating an electrical current. There's also a positive hole left by the N region by the absence of that electron. That's when the backfill movement occurs, where the electron from the P region fills the hole left in the N region. When the electron returns from the circuit through the bottom contact of the silicon, it fills the positive hole that was left behind in the P region. So that's a bit of a simplified version of the light to electricity conversion that occurs in silicon semiconductor photovoltaic cells. As was said earlier, most widely used photovoltaics are made of silicon, and that's what we'll focus on in this course. However, there are some other materials that can be used to create photovoltaic cells.